Okay. Alrighty, hello. So we are going to go over a couple of things that we didn't get to in class. So last time we spoke about remainder theorem, and we made the proof of remainder theorem. And so we're going to apply that. And we did this problem in class where we applied the remainder theorem to understand the role of zeros. And this is just a recall that, so remembering that if A, so I'm going to highlight this. So if A is a zero, of a polynomial, then the factor, which is x minus a, is a factor of p. Okay, so we have to determine, we're going to use this information to help us answer question 5. So we didn't get to this question in our class period, so we're going to take the time to do that now. So here, we're going to highlight this. So it says, consider the polynomial p of x. And so we have p of x equals x to the fourth plus 3x cubed minus 28x squared minus 36x plus 144. Okay, so that's a very long polynomial. And so it says that we're going to use remainder theorem. Using remainder theorem, is 1 a zero? Okay, so is 1 a zero of the polynomial p? Okay, so I already know that in order for this to be a zero, I need to get, I need to make sure that, p of 1, so when I substitute that, I need to make sure that that will equal a value of 0. Okay, so that's what we're going to do. So I'm going to substitute into this equation, or this function, 1. So I'm going to go ahead and do that, and I'm going to have 1 to the fourth power plus, oops, this is like my first time doing this, so sorry if I keep erasing and whatnot. Okay, so 1 plus 3 times 1 to the third, and then minus 28 times 1 squared minus 36 times 1 plus 144. Okay, so when you do that and you type that into the calculator, you will find out that that does not equal 0. Okay, and because that does not equal 0, we're going to say this is no. Right, so no, 1 is not a 0 of the polynomial because this did not equal 0. Okay, so in this case, if you want to see the work, this ends up being 1 plus 1 to the third is 1. 3 times 1 is 3. This becomes 1, so minus 28. And then minus 36 plus 144. Sorry, my pen is weird. And so we get 1 plus 3 is 4. 4 minus negative 28 is negative 24. Negative 24 minus 36 is 60, negative 60, and then negative 60 plus 144 will give us some other positive value that is not, minus, what did I say, 60 will equal, let's say we have 4, and then 84. Okay, so that will equal probably 84. Okay, so then because that does not equal 0, it is no. Using remainder theorem, 1 is not a 0 of this polynomial. Okay, so then moving on to the next question. So it says, using remainder theorem, is x plus 3 one of the factors of p? Defend your answer. Okay, so this is where we talked about in class, if we have x plus 3, Well, I know that in order for me to determine using remainder theorem, in order to determine whether or not it is indeed a factor, I need to actually set this into its 0 form. So I have x equals -3. Okay, so that's where I would set this equal to 0, and I get x equals -3. Now I would do the same thing. This time I'm going to substitute -3 into the function and determine if I get 0. Okay, so in this case, I would do p of -3 is equal to -3 to the 4th power plus 3 times -3 to the 3rd power minus 28 times -3 to the 2nd power minus 36 times -3 and then plus 144. Okay, and then when you punch this into the calculator, you will notice that you will get 0. Okay, so this will end up being 81 minus 81 minus 252 plus 108 plus 144. Okay, and so when you add these all up, you will get 0. Okay, so at that point, is x plus 3 one of the factors of p? We are going to say yes, it is. Okay, that's because we had 0 here, and this time we had like 84, so that's not, so remember when you substitute this back into the function, if we get 0, that means it is indeed a factor. Okay, so the thing is here, the graph of p, now we're going to see how this looks like on an image, right? So the graph of p is shown to the right. What are the zeros of p? Okay, so we know this very well. Okay, so that's where we look at our x-axis, and I'm going to use a different color, and we're going to see here what are the zeros. So we know we have a 0 here, a 0 there, and a 0 here, and a 0 right there. So let me get the same color here. So here we have the zeros when it's x equals -5, and then x equals, let's see, 1, or if this is, oh wait, no. Let me erase that. Sorry. Okay, going back. Okay, so I count here. I have 1, 2, 3, 4, 5, -6. So it's actually -6 here. And then here I have, and then here I have x equals, let's see, 1, 2, 3, -3. And then here I have x equals +2. So 1, 2. And then here I have, let's see, 1, 2, 3, 4, and then also x equals, when x equals 4. Okay, so those are my zeros. So then we can say here, we can say that our zeros are -6, -3, 2, and then 4. Okay, cool. And then it says write the equation of p in the factored form. Okay, so in factored form, this is kind of like our launches. So we're going to write p of x. Okay, and we're going to write a possible equation here. So assuming that we don't have a leading coefficient here, or assuming that the leading coefficient is 1, we can say that because these are the zeros, we can write the equation. So in this case, we can have x plus 6. So I'm going to take the opposite sign of this, and then we're going to have x plus 3, x minus 2, and then x minus 4. And that's my equation. Okay.